So, Newton's method, also known as the Newton-Raphson method or the Newton-Raphson root finder or Newton-Raphson root hunter or the Newton root hunter algorithm. It's a system for finding the zeros of a curve. You got a curve like this and you see that it's negative over here and it's positive over here, so it stands to reason there should be a spot someplace where it's zero, and you would like to know exactly where this is. If you have a calculator with a root or a zero function, it has to have a way to do this, and it doesn't do it by solving them algebraically. It does them with an algorithm, something like Newton's method. So let's see if we can explain how this thing works. To kick off Newton's method, you must take a guess as to where the root is, and the guess doesn't have to be all that good. I'm going to start with a pretty bad guess that, actually, the guess isn't on the curve like that. The guess is an x value way out here, which we call X1. It's our first guess. And we take that X1 and plug it into the function, whatever it is, and that gives us a y value, which I'm going to call f of X1. If this is 0, then hooray, your guess was correct and you're just done, but that's not what's happening here. If it isn't, the idea with Newton's method is that you're going to take a tangent line from that point that's parallel to the curve, tangent line about like that, and you're going to extend that tangent line all the way back until it hits the x-axis. Pull that line back. When it hits the x-axis, that becomes your new guess. This point is now x2. As you can see, this is still not at the root, but it's closer. And from here, we take x2, plug it into our function, and that gives us f of x2. If this is 0, then great, you win. If not, then try again. You take another tangent line. Let's go light green this time. Here's another tangent at the curve, and you extend that tangent line back until it hits the x-axis. That point is called x3. We plug that into the function. That gives us f of x3. Still not 0, but we're definitely getting closer. Take another tangent line. That tangent goes all the way back to, it's actually getting very close now, x4. And you keep doing that. You go x2, x3, x4, and while you're doing this, you keep an eye on the x values that you're getting. And if they're moving a lot, if this is going 30, 20, 15, 12, that means you're not all that close yet because you're still getting large jumps from one x to the next. But if you're calculating these x's and you start getting like 1.7624, and then you get 1.7623, and then you get 1.76291 or 4, these numbers are settling down, and it looks like you're very confident that your root is like 1.762, and as you do more and more steps, these numbers are going to move less and less. And eventually, when you have enough decimal places to make you happy with the answer, you stop and you say the root is approximately whatever your latest guess is. In most of our questions, we will tell you to do this cycle 3 or 4 times, or do it until you have an answer you're confident to the nearest hundredth. Something like that. So that's the general idea. You do these sawteeth where you keep moving in closer to the root, and the actual algorithm you use to find these x's, I can show you, or your instructor can show you if you want all the details of how the slope produces this and so on, but here is the rule that we're going to be using, and I'll just give it to you for now. The rule looks like this. It says, take your guess, x1 or x2 or whatever it is, and from that subtract the function's value at that guess divided by the derivative's value at that guess. And that becomes your new guess. So this says take x1 minus the function at x1 over the derivative at x1. That becomes x2. Now you run it again. x2 minus the function at x2 minus the derivative at x2, that's x3. Repeat over and over until you've got an answer, and you just watch that answer until it gets precise enough that you decide to stop. Okay, so this is a formula. You want to know how it works. I actually do not recall if it's on the formula sheet, so check that out. If it's on the formula sheet, great. If not, then you get to cram this into your head so that you have it available to you. So let's flip the page and we'll set up an example and see if we can get this thing to work. Okay, so we have a function. It's x cubed minus 2x minus 6. And we're going to need the derivative of that, so let's get that down right away. F prime of x is 3x squared minus 2. Okay, so we have our function. We have our derivative. And we're trying to find the location of this intersection point here. In the workbook, they use an initial guess of 2, which is very reasonable and it's very close. Just to show you what happens if we do something a little different, I'm going to pretend that 3 is my guess. I can see that's not a really good guess, but it doesn't need to be. We'll start at 3 and we'll see if this thing converges towards the same answer that the workbook gets. And for the record, before we dig in here, the workbook finds that 2.18 is the approximate root. So let's see if we get the same thing if we come at this from 3 instead. So the formula, to remind you, is that your next guess equals your current guess minus the function at your current guess over the derivative at your current guess. And I'm saying my first guess is going to be 3. I know that's a little off, but let's see what happens. So this says the new guess, x2, is going to be the initial guess, 3, minus the function at 3, which is 3, 9, 27, minus 6 is 21, minus another 6 is 15, over, and the derivative at 3 is 3 squared is 9, times 3 is 27, minus 2 is 25. Soon these numbers are going to be really ratty decimals, and I won't be able to do this in my head at all, so I'm just enjoying the opportunity to do one of them fast. 15 over 25 is 0.6. 3 minus 0.6 is 2.4. Okay, so from 3 we dropped straight to 2.4. There's a large correction right away. And now we run that whole drill again. I'll change colors a little bit to make these look different. The third guess is the second guess minus. Now I have to put 2.4 into the original function, and we're now in calculator territory. 2.4 cubed minus 2 times 2.4 and minus 6. I get 3.024 from that. Over, and now we do the derivative at 2.4. So 2.4 squared times 3 minus 2 is 15.28. Okay, 2.4 minus 3.024 divided by 1528. I get 2.20209. That's probably enough. Okay, so initial guess 3, next guess 2.4, third guess 2.20209. So it dropped again, but not by nearly as much. Let's run another one. I haven't made up my mind completely where I'm going to stop, but I'm keeping an eye on how much these change. And when they start to bog down and they're hardly changing at all, then I'll say close enough. Okay. Fourth guess is take this guess, 2.20209, minus, put this guess into the original function. So 2.209 cubed minus 2 times 2.2. I think I may have entered that first number wrong, so I just ran the whole thing again, and I get 0.27420 for the function. And now you put 2.20209 into the derivative, which gives 2.20209 squared times 3 minus 2. For the derivative, I get 12.54760. And when we crunch all that, minus 0.27420 divided by 12.54760, you get 2.18024. This feels pretty good because it's lining up with what the workbook said. So it's a little tempting to stop here, but let's run it one more time and see what happens. We're at 2.18024, and we'll do one more guess and see what the algorithm does when we're pretty much sitting on our answer. So we have 2.18024 minus, we put 2.18024 into the function, and out comes 0.00317 over, and the denominator would be 12.26034. And when we run that, 2.18024 minus hardly anything divided by 12. I get 2.17998, which is again pretty much 2.18. So you can't break this method by running it too many times. When it closes in rapidly at first, when it starts getting close to the root value, it settles down and just moves less and less. And if I ran 1,000 more steps, I think this would just settle at 2.179 something and just stop moving there. So that's the procedure. It's a little bit tedious. You can obviously speed it up by using memory features on your calculator. If you have a spreadsheet like Excel, you can grind these out very quickly by plugging in the formulae and just running them over and over. And this is how you solve equations that you can't do algebraically. You beat them down with what we call numeric techniques, like this one.